In this video, we are going to check out how to draw objects in 3 dimensions. All right, so the theory is called the VSPER theory, which stands for the valence shell electron pair repulsion theory. So we need to know how to draw molecules and represent their electrons and electron pairs. So the main idea of this theory is that you can determine the structure around an atom by minimizing the repulsion forces of the electron pairs. Recall that electrons are negatively charged and that they repel each other. Atoms can share electron pairs in a covalent bond, but they can also have their own lone pairs that do not participate in these bonds. So according to the VSPER theory, bonded and lone pair position themselves as far away from each other as possible to minimize this repulsion force. Everything is repelling. So this repulsion helps shape the structure of the molecule. So the steps for applying the VSPER theory is the first thing you're going to do is draw your Lewis structure. Then you're going to count the electron pairs surrounding the central atom, including both bonded and lone pairs, and arrange them in a way that minimizes electron pair repulsion. Do this by putting the electron pairs as far away as possible in 3-dimensional spaces. We've always probably thought in 2 dimensions, but we really need to think in terms of 3 dimensions now. So place the atoms bonded to the central atom at the end of their bonded electron pairs and determine the name of the structure from the position of the atoms and the lone electron pairs. We're going to have a nice table to do this. In fact, that's what we're going to do, so you can start to make one and draw one in your notebook. So this is what it will look like. There's going to be a number of columns to this. So total number of electron pairs, so that's everything put together. Our number of lone pairs. We've got our name of the structure, the bond angle. I've found a few examples, and then their 3-dimensional shape. So our simplest ones have 2 electron pairs in total and 0 lone pairs. This becomes a linear structure, and it's a 180-degree bond angle. So the example that I found was beryllium. Beryllium seems to bond with most things in group 7 to produce this linear structure. Looks a little something like that. And you can see that we've got 180 degrees going from, well, it's a flat thing, so we've got 180 degrees going around here, right? So this molecule has 2 electron pairs in total, 0 lone pairs. Everything would be inside the bonds. So our next one is going to have 3 electron pairs, and we have a couple of scenarios. So we can find molecules that have 0 lone pairs, and these ones are known as trigonal planar. They've got a 120-degree angle. Boron seems to bond pretty commonly in this shape, and you get a molecule that looks like that. So it's 120 between the molecule arms, if you will, but notice it's all flat. It's all in one plane. Now as well too, we can still have 3 electron pairs, but now we can have 1 lone pair. And so let's see what effect that lone pair is going to have. It's actually going to bend our molecule in a 120-degree fashion. Sulfur dioxide will have this one. So you can see how just having that 1 lone pair up top has bent our molecule down. So the molecule up here is probably a non-polar molecule, whereas this molecule now should have a dipole, and depending on where it would be, and so it would be a polar molecule. So continuing on to our scenarios where we have 4 electron pairs, again we can have 0 lone pairs, and we get what's called a tetrahedral structure, 109.5 degrees between our bond angle, and there's what our shape looks like there. So anytime you got an element like carbon that has 4, single pairs that are single atoms, electrons that it wants to bond with, it's going to end up in this shape. So carbon in that arrangement. Now we can also have something with 1 lone pair. This is a trigonal pyramidal, 107. And ammonia is a good example. So that just 1 lone pair now has caused our molecule to be sort of a flat thing we got going on here now. And as well too, we can have 2 lone pairs and we get a bench shape like water. So again, in terms of classifying these, I would say this would be a non-polar molecule. This one's probably leaning towards nonpolar as well, although maybe not necessarily. This one's definitely polar. You can definitely say it's got a dipole, and we got a positive and negative in there. Going all the way up to 5 electron pairs, we end up with something called trigonal bipyramidal, and we actually have 2 bond angles here. So it's just kind of difficult for us to put everything in perspective in one plane. So there's a couple of different angles. So we've got them in 120 and 90. If you have 1 lone pair, you get what's called a seesaw, and you can see how our shape is just slightly different there. 2 lone pairs is what we call a T shape, and that looks like that. So you can see it's all flat. It's essentially like a T with an extra line, I guess, in the back. And our 3 lone pairs, now we actually get back to a linear molecule, and you can see it there. We got the 180. So those lone pairs have a great effect on all of these molecules. And as high as we're going to go will be 6 electron pairs. So we have what's called an octahedral shape. Looks a little something like that. So we've got 6 bonds coming out of it. So we're definitely violating the octet rule when we make this molecule. If you have 1 lone pair, we get a square pyramidal shape. So you can see there's nothing on the bottom, one thing sticking up the top. And square planar is going to be our last one. And that is all in one plane, 90 degrees from here to here. When you encounter some of these structures in textbooks, it's probably a good idea to know what these different lines mean. A straight line just means it's straight. Then we've got a dotted, which is into the page, and then this little triangle. So a couple of examples there. That one has all 3, and so does that one. So it just gives it a bit of depth to it. And you might remember this page from your textbook. Page or pages, I should say. This is 209 and 210. And these are all the scenarios that we covered. So essentially every molecule I ask you, you're going to have to kind of figure out which structure it is. So you're going to have to be able to draw it and then just look at this table and figure out, which scenario it is applied to. That's about it.